probably I have to go very quickly just because there are a lot of stuff. The controls readily, what the system does, again, if we go back to this picture, what the system does at this level is pretty simple. It will repeat infinite number of times. Just as soon as you start it, it's going to repeat doing inference. In each inference cycle, the following step: first, it picks a node randomly. But this randomness is biased by the priority value. So high priority value means a higher probability to be selected. Okay. So it's not activated altogether. It's not just one at a time. They're all activated, but with different frequency. You can think about it. Okay. Of course, it's implemented as time sharing, okay, but with different priority. And also, wherever you pick, for example, this time I pick Slim. And then the next step is I'm going to pick a task and a belief. That is, I pick a red link and a white link. Usually, there are a lot of them, both types. Again, it's prioritized. Okay, some tasks may be more active in my mind. As soon as I think about swimmer, I'm going to think about that thing. Some others are relatively low priority. It's still there, okay? It just, I'm not going to think about it very often. The same thing for belief. For example, for bird, I may know 1 million things, but it doesn't mean wherever you mention bird, I'm going to think about all. For example, the most frequent association may be, it flies, maybe that's more often. There are some other property which I know, but I don't think about. So after you pick a red one and a white one, you see it's guaranteed that they share a term. That's the node you're working on, right? Otherwise, you cannot find this. So because of that, according to the previous pattern, you know for sure there is an inference rule that can be applied. Which one is completely data-driven? Okay? If you pick this tool, this is the subject, this is the predicate. What you get is the inductive pattern. Then you do induction. Okay, if you get this tool, and that's a deduction. So the system does not really pick an inference rule. It will trigger the inference rule using the task and belief that happen to be selected at the time. Okay, this is very important. Then you derive a conclusion. Usually, actually, you can derive several conclusions, which I didn't mention in previous. But anyway, you derive a conclusion, you put the conclusions back into the system, then you just repeat that process. Roughly speaking, that is what is going on. So that's the control mechanism I have already mentioned. So now clearly you can see that one thing, compare this with the traditional system. One thing is you do not design in advance a sequence of operations for your system to carry out for any given task. You kind of like throw the task in, you like it, kind of like free association to happen, but this free association is prioritized or biased by your past experience. It's not really, equally, everything is equally possible, which you don't have the time to do. That's one thing. Another thing is the actual path they actually take is almost completely determined by the current priority distribution. So the next question is who decides the priority distribution? That's a big question, and priority is determined by a lot of factors. Here I just mentioned a couple of them. For example, when the user provides a task to the system, you can provide an initial priority. It's kind of like you can tell the system, okay, there are 3 things for you to think about, but this is urgent. This tool you can just put in the back of your mind. You think about it when you have the time. Okay, you can do that kind of thing. But that's just your opinion. The system may have a different opinion because, for example, if one of them happen to match the system's current internal interests, then that one may also get some free energy so that it will be actually processed faster than the one you specified as a tool. But anyway, so that's another factor. Other factors include, for example, amount of knowledge. Truth value clearly matters. everything else being the same. Okay, this one, I'm pretty certain. This one is just a pure guess. You can see the difference in the confidence level. Okay, that clearly influences their priority. Okay, if you have limited time, you want to think about the sure thing first. That's more reliable than the other stuff, which you may want to take into consideration when you have the time. But that's, again, only one factor. Another factor is maybe something not very sure, but they happen to be useful in the past. Then you get a reward in that way. Okay? It works last time, so I will try it again, compared to something else which everyone said it's good, but it didn't work for me in the past. And so I may actually give it a lower priority. So you see, all those things are combined into the priority calculation. And another important factor is all those things change over time. So overall, you don't have a repeatable internal environment, which is where it comes from. The system, when you actually run the system, you will see it looks like unpredictable. But that unpredictability is not coming from some fancy random number generator. It's coming from the fact that the internal environment changing in a non-repeatable way. It's not a circular environment which you never go back to your past. Okay. So for that reason, the same question, if you gave it at a different time, you may get a different response, just because the internal environment has changed. So that's a very brief description about the control strategy. And then they're all summarized into this slide. The system architecture in a very high level is just a memory. A memory is nothing but that conceptual network. And then there is a buffer of the new income task. Okay, then the input will go first into this buffer. You see, this kind of box means a selection point, okay, or a filter. Only some of them will go into the memory because, again, resource computation. You don't have the time to think about everything. So some of them will get integrated into the memory, and in each cycle, you select from the memory according to the method. You only pay attention to some of the tasks currently in your mind. And you get the conclusion also go back into buffer, compete with the other things. So only some of them will get reported to the user, not all of them. So that's a brief description about what's going on. So, and the whole system, of course, is much more complicated than the picture I just gave you. And what I gave you, roughly speaking, is what we call layer 1, because the system is built layer by layer. In each layer, we extend the logic. We put more complicated grammar rules into it, so it can express more complicated things, and we put more inference rules into it. So overall, the current design consists of 9 layers. What I explained is the layer 1. That's the core. Okay? But this is different from the modular structure because each of the layers will use the previous layer as foundation. So you build on them one by one. You don't build each layer independent of each other. So in the implementation, you only see this part. This part is kind of like part of the meta logic or the idealized version, which I'm not going to spend time on. Very roughly speaking, I can tell you what each of the layers adds. At the basic level is what we call, we only have atomic term and a single coupler. Then in layer 2, 3, and 4, we have compound terms, and we have derivative coupler, that is multiple relationship. And also a term, that's a crucial thing. A term is not necessarily a word. It can be a structure. It can be a complicated structure. It's just like, we can still analyze natural language into subject and predicate, but each of them is not a word, it's a phrase. Okay, phrase can contain phrase and so on. So, yeah, I have a summary here. So the extensions happens, you can have compound term with internal structure, and also a statement in themselves can be treated as a term. So you can have what? You can have a sentence about a sentence about a sentence, and so on, in a recursive way. Then we introduce the concept of events. Events are statements with a temporal truth value, meaning that the truth value would actually have some time step attached to it. So it's true now, but it was not true before, and it will not be true again in the future. That kind of thing can be represented in this language. And then we have operations which are special events, which are realizable by the system itself. So for example, I raise this cell phone to you is an event. To me, it's an operation. That's something I can do. I can make it happen. Okay. And then, well, you can begin to feel the relationship with a robot, which has directly happened here. You just not sit there, just answer questions. Okay, you begin to do things in the world. And also, goals are the events to be realized. That's things you want to do, either directly or indirectly. So all of those are fully integrated into this logic. So many of the ideas come actually from logic programming, like Prolog, that kind of thing. So you can treat operation as reasoning. It just, in my system, it's not just binary deduction anymore. It's uncertain. It can be induction, abduction, and so on. They're all mixed together. So now, if I have operation, how about perception? Actually, I'm taking a position which is also raised by several people in the cognitive science. That is the opinion that perception actually can be treated as a form of operation. What I mean, well, that's actually the paper this time we present at Prague. Is subjective. Perception is not a way to kind of like represent the world as it is. Instead, it's a way to represent the world as you see it. Why? Because what you get depend on, of course, depend on the sensor, what type of sensor you have. Not only that, also depend on what kind of concept you have in your mind. What's your current belief? What's your current goal? What is your current attention allocation? All those things matter. Of course, the world is still there and still gave you the initial raw material, but the processing is kind of your processing. So it adds up with your impact on it. So it's fundamentally subjective. So you don't see the world as it is. The second one is active. You're not sitting there just wait for the information to flow in, or like many current machine learning work. It just you get photos, you scan them. It's not like that. For example, vision, according to this point of view, you are going out, you are paying attention to different part of the world, you are getting that information back. Okay, that's your action. The consequence is the result of your own action. And also, it also means that within the internal representation of this kind of perceptive results, there are operational terms you'll see. Actually, we have a description in our paper, that is the coding itself. For example, when you code a human face, it's not just a pixel of points. You are actually scanning it. Okay? We have a lot of psychological evidence supporting that. So what you remember actually is part of like scanning trees and with the consequence. So that's our opinion. And finally, it's unified in the sense that perception is not carried out by a completely separate module. Instead, it's fully integrated with the other mechanism I just mentioned, for example, reasoning and learning. Yeah, I didn't mention learning. Actually, we have another paper in a previous AGI conference just argue that reasoning and learning is actually the same process. Well, as far as that's true in NARS. They don't have a module for reasoning and another module for learning, and then they communicate with each other, not at all. you see all the rules I provided before actually carry out the learning process. You can call it learning, you can call it reasoning. Again, that's my picture, when you see it from different angle, when you stress on different aspects, you get different results. You can legally label them with different words, but that's not the reason for you to claim that there are two separate processes going on. Okay, that's actually, my point of view is, I believe everything is actually unified, tightly unified in the system. That's how we build this system. So, now how about the raw data? In sensation, this is something we recently start to experiment. So we also allow some kind of like array representation or matrix representation to come in as a raw data. So, but we somehow turn it into NARS statements, so it can be integrated with the presentation. So this whole matrix can be a term. Each individual cells in it also can be treated as a term. And then we can have some kind of operations on this kind of representation, which, so see that now this picture of memory is different from the previous network. And I think this is closely related to what Professor Kella just presented before. It's a structure with linguistic items, conceptual items, and sub-conceptual items. You see in this picture what we have, the one that I deliberately picked the meaningless name and what we can call internal terms. Every node here is still a term. It just, this term does not necessarily directly relate to anything outside the system. It's an internal abstraction. On the other hand, there are some of the terms that directly correspond to English words. There may be some other terms correspond to directly into Chinese words if the system understands this language. And also some of the terms directly correspond to a mental image or raw, the image you get or vision you get. It's different level of abstraction or simplification. And the relation among them, you see, it can be the inheritance relation I mentioned before. Is a type of something else. Okay? And now you can recognize some of the internal thing. You can recognize what this actually means according to its relation with the other stuff, as abstraction or generalization stuff. And then we also have another type of relationship, which currently we call it represent, or you can call it symbolize. That is the relation between a word and a concept that can be represented by that word. And that relation we know is a many to many. It's not a one-to-one mapping. Okay, you can use one word to refer to several different concepts. And the same concept can be represented by different words, even in the same language. So you see, it's kind of like we're working on the same type of internal representation, but the difference is here, I guess the relation are closer. We don't have a clear separation of the three different types, even though you can still see a weak, a fuzzy boundary among them. And also their processing are consistent in the sense that we use the same group of inference rules, all of them. For example, deduction. Typically we think that they're among, say, linguistic terms, but it doesn't have to be. It can be also among the image. Okay, if one image is a simplified version of another one, and then I have a third one which is a simplified version of the second one, of course you also have this transitivity. The same thing is true for the other type of inference. What is missing in the picture is just because I don't know how to draw are the operations. The operations should also be there. Okay, some of the words, especially the verbs, their meaning are actually directly grounded to what the system can actually directly do. Okay, that's the operations. So let's talk about what type of inference we can do. One thing that's another AGI paper we write It's about we use this logic to use reasoning to do or to model classical condition. Okay, you know this, the well-known Pavlov dog. Okay. So it's basically you have an event which is followed by another event. Then the system will form a hypothesis, say that I guess this two may be related to each other. And in the future, you'll see the first one, you'll form an anticipation for the second one, which can be correct, it can be wrong, but some of the relation will be strengthened by repeated patterns, and some of them will be rejected. So this is also what we call anticipation, which is, I think, also directly related to Dr. Chana mentioned expectation. When you do recognition, okay, you recognize part of it, then you form a expectation about the other part, which if it's confirmed, then go back to reconfirm the one you have perceived before, and then eventually you get a strong feeling about what you are seeing. Anyway, so we can do this. And operational knowledge, how is that represented in the system? Yeah, we see, well, since everything is reasoning, of course, we need to represent the so-called procedure knowledge also in the form of statements. Okay. For example, a walk operation. Okay, we can represent that as some kind of relationship, but this relationship is something the system can actually realize by itself. And the argument it takes is a source and where you start, and destination, that's where you want to go, in the simplest case. Okay, you walk from point A to point B. Then what kind of knowledge you can have? You can also have inheritance relation among those operations. For example, you can say walk is a form of move. Okay. So this is the inheritance. But you can also have another relation. This is what we call implication, which is more like causal relationship. So with that, you can represent the condition, precondition, and consequence of each of the operations. Of course, it's true to a degree according to your experience. Okay. In this case, if you're at this place, then if you move to the other place, then at the end you're going to be at the other place. If everything goes as planned. Then what? Then, yeah, some people say, yeah, logic can only do abstract things. How can you handle sensory motor and perception action and so on? What we have is, our position is we do not build, NARS is not designed as a robot, of course. It's a reasoning system. But we want it to be able to be put in theory into any robot because we assume there are some operations. We can do reasoning about the operations, but on the other hand, we do not assume the concrete nature of the operation. For example, you can have a robot with 2 legs. That's a bunch of operations which control the legs. If you have a robot with 4 wheels, then you have another type of operation which control the wheels, which are very different from the leg. Okay? But in terms of reasoning, our belief is the logic are the same. Okay? You have perception, you have action, you have goal. You try to reach the goal, and you try to combine your operations according to your experience and to reach the goal, whatever it is. So the idea, actually, our ambition is to build a universal or general purpose mind for all types of robot body. So you can plug it in. Of course, it's not going to run out of the box. You need to train it. That is to learn from its mistakes, errors, fail down over time, and so on. But gradually, it will learn how to manipulate its body to achieve its goal, whatever it is. So for that reason, in the system currently, we already have what we call a sensory motor interface. So it's kind of like, I don't need to understand how it works. It's just like, we don't understand how this thing works. We have a remote control. Okay, there are 5 buttons. I know if I press this button, something will happen, I will see that. I don't know the inside magic. Okay. So this interface is going to allow you, which is a robot device, to tell me, okay, I have 5 operations. You just remember me as A, B, C, D, E, F. Okay? That kind of thing. And then you try me, you will see what will happen, then you will learn in what situation you're going to use it. So that's kind of like the general attitude. Of course, if you already have a detailed manual, gave to me in the first place, you tell me, okay, this A is going to do this, this, this. Of course, that will be even better. Okay, I will just code that into my BD. But even if you don't give me anything, I can still try this. And also, even if you give me a manual, I'm not going to completely believe you, okay, because I'm not axiomatic, okay, even if your words is not taken to be absolute truth, I will still try it using my own experience. So that's basically, yeah, we also invent a name called NARS Plus. That means NARS plus some additional plugin. Okay, so if you put NARS into Pepper, that will be one form of NARS Plus. If you put NARS into Now, that will be another type of NARS Plus. The logic remains the same, the body can be completely different.